We've looked at solving our systems of equations by substitution and by the addition method. We want to look at one other way, one other method, and this is using determinants and Cramer's rule. Now, a determinant we use with what we call square matrices. So if we have a matrix, and all that a matrix is an arrangement of rows and columns. A square matrix is where your number of rows and your number of columns are the same. So here we have a square matrix. We have 2 rows and 2 columns. To find the determinant of this 2 by 2 matrix, what we do is we find the product of the diagonal going down, that would be AD, and we subtract the product of the diagonal going up, CD. And that would give us the determinant for that 2 by 2. Now, it's very important that you get your diagonal going down first, then you subtract your diagonal going up, because this is not commutative because it's subtraction. So if we had our matrix 10, 9, and 6, 5, and we want the determinant of this. Well, our determinant would be equal to the product going down, which is 50, minus the product going up is 54, which is -4. If we had the matrix 2, 4, -3, -5, and we want our determinant. Well, our product going down is -10, minus our product going up is -12. Well, minus a negative is a plus, so this would be 2. So it's fairly simple to get a determinant for a 2 by 2 matrix. Now, in a little bit, we'll look at how to find the determinant for a 3 by 3, and that's a little bit more involved. The bigger your matrices are, then the more involved it is to find the determinant. Okay, what we want to use then is what we call Cramer's rule. And Cramer's rule. And so we're going to start with the 2 by 2, 2 equations and 2 variables. So if we have an equation in the form of a sub 1 x plus b sub 1 y equals c sub 1. So we've got our equation here, two variables, and then we have a second equation and I just used subscripts to show that they came from different equations. What we want to do is to set up the matrices so that we can then find the determinants for these. Well, we're going to talk about our matrix to find the x. What we will do is we will find our matrix for our numerator, and sometimes this is actually called, we're going to get the determinant for the variable x over the coefficient determinant. That's going to be our x. Our y will be the determinant for y over our coefficient determinant. And sometimes you'll even see this terminology. You may be asked just to find d sub x, the determinant for the x. Now, what we do when we find this is we set up, and when we do the determinant for the variable x, what we do is we are only going to write down our coefficients and our constants. But if we're solving for the x, then we do not write down our a coefficients. What we do is we write down in place of them our constants. So if we look at this, our constants are right here. So when we write this down in our determinant, we're going to start with our constants because that's where the x would go. Then we will put the coefficients for our y. So that's going to be the determinant for the variable x. Now, the coefficient determinant is simply your coefficients for your x. And your coefficients for your y. So you notice in both of those, and we're solving for both the x and the y, the denominator's the same. And it's what we call the coefficient determinant. But in the numerator, what we have is we put our answers in place of the variable that we're solving for. If we're solving for the x, then our answers go in place of that. Okay, when we're solving for the y, then for our determinant, okay, we'll write down our a's, the coefficients for our x's. Then in place of our y's, since this is the variable that we're solving for, we put our answers, or our constants. The denominator, again, is the same as what we had. It's our coefficient matrix. So again, even if I didn't have my x and y out here, you should be able to tell which variable I'm solving for simply by looking to see where the answers are. If the answers are in place of the x, then you're solving for the x. If the answers are in place of the y, then you're solving for the y. Then once we've done this, we're simply going to find our determinants. So let's look at a problem. Leave that there. And let's go and look at this one. We're going to solve this by Cramer's rule. So the first thing we have to do is set up our matrices. So for the x, okay, in the numerator, in place of our x's, we'll put our answers, 12, 24. Then for our y's, we put our coefficients. For the denominator, we put our coefficients, so 5, 3, 4, negative 6. Now, we're going to go through and we're going to find our determinant. So we'll get the product going down of the diagonal going down. That would be negative 72 minus the product of the diagonal going up, which is 96. Negative 72 minus 96 is negative 168. Okay, for our denominator, it would be negative 30 minus 12, which is negative 42. Now, if we divide negative 168 by negative 42, we get a positive 4. So x is 4. It's a very neat way of finding your x's and y's. And you find them independently, so one doesn't depend upon the other. Okay, for the y, we want to set up our matrix, so we'll put our x, and in place of our y, we put our answers, or our constants. Now, the denominator is going to be the same as what we got up here, and what we got up here was negative 42. So we don't have to go through and actually do the denominator again, because it's not going to change. So we would have 120 minus 36 over negative 42, which is 84 over negative 42, or negative 2. So we have as our solution 4, negative 2. Now we could always check this by substituting back in. 5 times 4 is 20, minus 8 would be 12. 12 plus 12 would be 24. And so we got the correct solution. It makes both of those true. So it's fairly easy to use Cramer's rule to get our values. Now there's times that, if you remember back with our systems, we got to where there wasn't a solution. If you remember when we dealt with systems, our choices were that we had either two lines that intersected. That's not the one I want. We had either two lines that intersected, so we had a solution. That's like what we just did. we had two parallel lines, so there was no solution, or we had two lines that were the same on top of each other, and we had an infinite number of solutions. And we saw when we did it by the elimination method or by substitution that our variables dropped out. And when they dropped out, we either had a true statement or a false statement. Well, it would be nice to know with determinants, with Cramer's rule, how to know if we have solutions or if we have no solutions. And so let's go through and look at one. And by my saying all that to begin with, you can pretty well be sure that this is going to come under that category, but you just need to know how to recognize when that happens. So we have 3x equals 2 minus 3y. Okay, 3x equals 2 minus 3y, and 2y equals 3 minus 2x. Okay, first of all, we need to rearrange these. So we need it in the form of ax plus by equals c. So I would add the 3y. And here I would add 2x. Now we'll set up our matrices. So we would have, in place of our x column, we would have our answer column, and then we have our y column. In the denominator, we have our coefficient matrices. Okay, we've got 4 minus 9 is negative 5. For the denominator, we have 6 minus 6, which is 0. Now, we know we can't divide by 0. So this tells us that there's something that we're going to have to deal with. So this is what happens. If you have, when you're doing this, if you've got some number, we're going to just say a number, c, and your denominator is 0, but you have a numerator. It's not 0. So this number is not 0. The denominator is 0. Then this is going to be inconsistent, which means you have parallel lines. So there's no solution. That's what inconsistent means. There's no solution. Okay. If your denominator's 0, so your coefficient matrix, your D, is 0, and your numerators are also 0, both numerators are 0, then that says that there's going to be an infinite number of solutions. So this is when they're on top of each other, when it's actually the same line, and they would be on top of each other. And so then again, what you would do to write your solution, it would be the set of all x, y's, such that, and then you simply would write one of your equations. So this one up here, since we had a numerator, but our denominator was 0, then there's no solution. But if they had both been 0, then it would mean that it was the same line and we would have an infinite number of solutions. So it's fairly easy to tell with the determinants when you have a solution or not. Okay, we want to look just a little bit at what to do when we have 3 equations and 3 variables. And that gets to be a little bit more involved. We've got to first of all look at how to find the determinant. Now there's 2 ways of finding the determinant. One way seems fairly easy, but it's not the way that I usually recommend because of some other things that go along with it. The idea behind this one is you deal with your diagonals. So we would have our a sub 1, a sub 2, a sub 3, b sub 1, b sub 2, b sub 3, and c sub 1, c sub 2, and c sub 3. Okay, what you do when you're doing it by diagonals. Now you can go through and learn a pattern, but to me that's a little bit harder. What I was taught to do is to go ahead and write down my first two columns again. Okay, then what we're going to do is we're going to find the products of the diagonals going down. So as we deal with our diagonals going down, and we're going to add those up. So that would be a sub 1, b sub 2, c sub 3, plus b sub 1, c sub 2, a sub 3, plus c sub 1, a sub 2, b sub 3. So we found the products of our diagonals going down. From that, we're going to subtract the product of our diagonals going up. So it's going to be the product of our diagonals going down, the sum of our diagonals going down, and then we're going to subtract. Now, if I could put parentheses here, but we're going to end up subtracting each one. So we're going to subtract a sub 3, b sub 2, c sub 1 minus b sub 3, c sub 2, a sub 1 minus c sub 3, a sub 2, b sub 1. And this is a way that we have of finding our determinant. Now, there's another method, and I like it a lot better, and there's a lot of different uses for the ideas behind this method. And so I'm just going to go through one problem here. We'll find the determinant, and then I'm going to show you the other method, and that's the method that I will use as we go through, because I think it just works out just a little bit easier as we work with it, and you don't have to work so hard. So let's do one by this method, and then we'll look at a different method. Okay, if we take this matrix, we want to find the determinant. Now, I don't recommend trying to memorize all of this pattern. What I would recommend if you're going to do this method is to write down your first and second column. So we're going just right here at the end, put 2, -5, -4, and 1, 6, 3. Then we're going to multiply our diagonals going down. So as we do that, we've got 2 times 6 would be 12, plus, well, this next one's 0. Anytime it's got a 0 in it, that's nice. Plus, then 7 times -5 times 3 would be -105. Now, we will subtract all of the diagonals going up. So we'll get the products of these, but we're going to be subtracting them all. So our diagonals going up, okay, we've got -4 times 6 times 7 is a -168 minus 0 minus a -5. And if you go through and you combine all of that, you get 80. So it's a method, and it's a nice method, and it will work. But there's another method that we have that's called expansion by minors. And it works in a lot of other things. If you go into finding inverse matrices, then you may want a method of expanding by minors, and so you would be used to it. So let's look at doing some of these by expansion by minors. And this is what we deal with when we're working with our matrix, and we're going to do it by minors. The first thing is we need to set up our matrix. So let's say we have a sub 1, a sub 2, b sub 1, a sub 3. B sub 1, B sub 2, B sub 3, and C sub 1, C sub 2, C sub 3. All right, when you do it by minors, you can expand it about any row or any column. It doesn't matter which one you do. So usually what you do is you look for a row or a column that has zeros in it because that makes it a little bit easier. Then you also deal with the sign of each term. Each position has a specific sign. In this one, it's plus, minus, plus, minus, plus, minus, plus, minus, plus. You always start with the plus and then you just alternate. And you carry that alternation. It's kind of like a wraparound. You just continue to the next row. So if we had a 4 by 4, we'd have plus, minus, 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 plus, minus. So it just depends on a 2 by 2, plus, minus, plus, minus. And that actually came into play when we did our determinant. But you can pick whichever row that you want or whichever column. Now what you do first of all is you write down the sign for that position. So I'm just going to do it about this first row. So as I do, the sign for the A sub 1 is a plus. So I'm going to put a plus and then whatever my A sub 1 is. Then that's going to be times, and since I'm doing this row, then what I do is I'm going to omit that row and that column that contains the A sub 1. And what I'm left with is a matrix that's a 4 by 4, or 2 by 2. So that would be B sub 2, C sub 2, B sub 3, C sub 3. Okay, then we're going to go to our next number in that row. Okay, when we go to that next number, that B sub 1, well, it has a minus. So we put down the sign of the term, then we put down whatever B sub 1 is. Then what we're going to do is we're going to eliminate the row and the column that has the B sub 1. Well, we've already marked out the row. And so now we're going to eliminate that column. And I guess let me try doing this. So it's going to be everything that's not in the yellow. That might be one way of looking at it because I couldn't undo that green that I did. So that would be A sub 2, C sub 2, A sub 3, C sub 3. Then we go to our last number, and that position is a plus. We put down whatever that number is. Then we will eliminate that row and that column, and we'll deal with the matrix that's left when we eliminate those. So that's A sub 2, B sub 2, A sub 3, B sub 3. And this is called expanding it by minors. When we get into a 4 by 4, then we would do the same thing. We would pick a row and we'll deal with the sign of that number, and then we eliminate the row in that column, whatever row and column that we're working with, and we eliminate it and write down the matrix that's left. And so it doesn't matter how big your matrices get, you can still find the determinant this way. So let's take one. 2, 1, 7, negative 5, 6, 0, negative 4, 3, 1. Now, since we can pick whichever row and column we want to, I always like to pick one that's got a 0 because that's going to make it easier. So I can either pick this last column or this last row. It doesn't matter which one you do, you're going to do the same process. So let me just pick the middle row. This is the row that we're going to use. Now, as I deal with this row, this first number, its position is a negative. So I'm going to put minus, and then whatever my number is, which is -5. And then I'm going to put down the matrix when I eliminate that row and that column. Well, that would be 1, 7, 3, 1. Okay, my next number, the position is a plus. I'll put my 6. Now I'm going to eliminate that row and the column with the 6. So that leaves me 2, 7, -4, 1. Then I've got that position is a minus, and I have a 0. And here it's not really going to matter because 0 times anything is 0. So it's not necessary, but if I wanted to go ahead and put it down, it would be 2, 1, -4, 3. And that's why you pick rows with zeros, is because that's simply going to be 0, so we don't have to deal with it. So what we have is 5. Okay, our product going down is 1 minus our product going up, which is 21. Then plus 6 times 2 minus a -28. So we have 5 times -20 plus 6 times 30. So -100 plus 180, which is 80. And if you look back, we just did one while ago where we did this by diagonals, and we got the same thing. But we did it by a different method, and I'm not sure which one of these is my diagonals. Oh, right there. Well, no, that's the one there. We went through, we got the same answer, but we had to do a lot more computations. And as you get used to this method, especially if there's a lot of zeros, it becomes a little bit easier and it moves a lot faster. And as I said, we can use it on some other things as we go through. So let's look at solving a system using Cramer's rule. And as we do, I'm going to do these expansion by minors and come up with my determinants. Okay, here's my system. So I'm going to find my determinant for x, and I'm going to divide it by my coefficient determinant. So that's going to be, in place of my x column, I'll put my answer column, 16, -9, 2. Then I'll put my y column, -2, 3, 4, and then my z column, 1, -1, 3. Now, if you notice, we didn't have any zeros, so we're going to have to do the whole thing, but it's okay. For the denominator, it's 3, 2, 1, -2, 3, 4, and 1, -1, 3. Now, I'm just going to do it about this first row. Usually if I don't have a 0, I just go ahead and do it with the first row. So this is going to be 16. Now I'm not going to write the whole matrix that's left. This is our matrix that's left right here when we eliminate the first row and the first column. So what I'm going to do is go ahead and just do that computation. The diagonal going down is 9 minus the diagonal going up is -4. Then it's a minus. This is plus minus plus. -2 times, okay, eliminating that row and that column. Well, I have -9 times 3 is -27 minus, okay, I've left out this row and this column, 2 times -1 is -2. Then it would be a plus. My last number is 1. So I'm going to leave out this row and this column. So that's -36 minus 6. Now I like to go ahead and just do my computation underneath it, and we'll have some room down there to do this. So we've got 16 times 13 plus 2 times negative 25 plus 1 times negative 42. I'm going to show you something at the end that's kind of neat. So 16 times 13 is 208 minus 50 minus 42 gives us 116. Okay, now for my denominator, I've got to do the same thing. So I have 3. Okay, I'm going to leave out the first row, the first column. So I have 9 minus negative 4 minus a negative 2. Okay, leaving the first row in the second column, that would be 2 times 3 is 6 minus a negative 1 plus 1, first row, third column, so 8 minus 3. So this is 3 times 13 plus 2 times 7 plus 1 times 24. So we have 39 plus 14 plus 24. That's an 8 minus 3, not 8 times 3. So this is a 5. And I'll show you something in a minute that would have helped us check and find mistakes. I should have known that wasn't an 8 times 3, but a minus. But my marks don't turn out real nicely, and so I sometimes mess it up. But I'll show you a way that we would have caught that mistake, other than I've already got it written down. So that's going to be 58. So our final answer is negative 2. Okay, we go to the y's. Now, one of the things is we've already done the denominator, so we're not going to have to do it again. So we're going to set up for our y. We put down our x's. We replace our y's with our answer. And we put down our z's. Our denominator will be the same as what we just found, which is 58. So we're not going to go through and do our denominator again. Okay, I'm still going to use that first row. Since I used it up here, I'm going to use it in all of them. So I've got 3 times negative 27 minus a negative 2 minus 16 times, okay, first row, middle column, 6 minus a negative 1 plus 1 times 4 minus a negative 9. So this is going to be 3 minus a negative is a plus times negative 25 minus 16 times 7 plus 1 times 13. So negative 75 minus 112 plus 13, and that turns out to be negative 174 over 58, which is negative 3. That's my equal sign. So that's actually a positive 2. I'm running out of space. So that's equals positive 2. Looked like a negative 2. Okay, then we want it for our z. So we're going to set up our determinant for z, which means we'll put our x's. So 3, 2, 1. Our y's, negative 2, 3, 4. In place of our z's, we'll put our answer column. 16, negative 9, 2. Our denominator is still going to be 58. It doesn't change. So going about the first row, we've got 3. That would be 6 minus a negative 36 minus a negative 2 times 4 minus negative 9 plus 16 times 8 minus 3. So we've got 3, that's minus a negative, makes that a plus. So 3 times 42 plus 2 times 13 plus 16 times 5. So we end up 3 times 42 is 126 plus 26 plus 80 would be 232 over 58, which equals 4. Now, I said earlier there's something that we can do that helps us catch mistakes if we make any. And I made a mistake there. I put 24 up here. I said 8 times 3 instead of 8 minus 3. And one of the things that you can notice is we've got some numbers that are the same. In these parentheses, because we use them to get those same values, we have a 13 and a 13. We have a 7 and a 7. We have a 5 and a 5. We have a negative 25. This was the answer we got when we did what was in the parentheses. We have a negative 25, and I need to go back up. I have a little bit more up here, and a negative 25. Let me go and catch this 13 and 13. And I don't have what I've got left here. I have a negative 42. And I'll have an opposite, positive 42. The last one on the first determinant and the first one on the last one will be opposites. Other than that, you'll always match up because you're using all these same equations. So that's one thing when you get done, I usually go through and check, and that helps me know then if I've made a mistake. What we're going to look at now is where we have a matrix and we're told what the determinant is of that matrix, but we're missing some of our values here. Like we've got this x right here that we don't know what it is. So we want to solve for that x. Well, since we know what the determinant is, we can go through and set this up to find our determinant. So let's just take the first row. Even though we've got a 0 here, we can take the first row. I like to take the row that has the variable in it. So we've got 2 times, we're going to eliminate that row and this column, so that would be 1, 0, 1, 4. So the product going down is 4 minus 0, the product going up. Then minus x times, the product going down would be negative 12 minus the product going up is 0, plus 1 times negative 3 minus 2. And that equals 39. So what we have is 2 times 4 minus x times negative 12 plus negative 5 equals 39. Well, working this out, we have 8. And this would end up being plus 12x minus 5 equals 39. We just have an equation to solve. 12x plus 3 equals 39. Subtracting 3, 12x equals 36. So x equals 3. So if you had something and you had a missing term, you didn't know what that was, then you can still set it up to find your determinant and solve for that variable. And we want to take just a minute and go through one determinant for a 4 by 4. Okay, here we have a 4 by 4, 4 rows and 4 columns. We want to find the determinant. Now, what we're going to have to do is to break this down into a smaller matrix. So we're going to pick a row or a column to expand it about. Well, what I look for are zeros. And I've got a column right here that's got 3 zeros. That makes it very nice. Now, if I hadn't had that one, well, I've got one with 2, and that would be okay also. But I'm going to expand it about this column. Now, when we looked at our signs earlier for a 4 by 4, it was plus, minus, 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 plus, minus. So my signs for that column, they're all minuses. But it's not going to matter for those 3 because they're zeros. So I'm going to expand it, and I'm going to do it about the 2. So I'm going to eliminate that row and that column, and that's actually the only one I'm going to have to do. So it's going to be a minus 2 because that's the sign of the position. Then I'm going to do it times the matrix that's left when I eliminate that row and that column. So that's negative 2, 4, 1, 5, 0, 5, 4, 0, negative 1. Okay, now I want to do this matrix, and I want to find my determinant for it. Well, again, I can look at my columns and decide which one to do it about. This one looks real nice because it has a bunch of zeros. Well, if I think about my signs for that column, it's plus, minus, plus, minus, plus, minus, plus, minus, plus. So if I'm going to do it about that column, then these are the signs that I'm going to use, but it's real nice because all I need is the 4, so I just need that one sign. So I'm going to expand it about this column, and I want the matrix that's left when I eliminate that row and that column. So let's look at what we have. We've got negative 2 times, and then I'm going to have negative 4, and then it's going to be the matrix that's left. Once you get down to a 2 by 2, then you can just do the product. So that would be negative 5 minus 20. So negative 2 times negative 4 times negative 25. So that would give me a negative 200. Now, if we hadn't been fortunate enough to have columns that had 3 zeros or, just one number and the rest zeros, then we would have had to have done a little bit more work. If suppose we had done it about this row, well, that would be our negative 2, then times negative 5. We would have left out this row and this column. So that would be 4 times negative 1 minus, we left out this row, this row and this column. So 0 times 1 would be 0. Then it would be the 0, so that wouldn't matter. It was still plus 0, but we don't have to do anything. And then a minus 5 times, we're going to leave out this row and this column, this row and this column, so that would be 0 minus 16. So we have negative 2 times negative 5 times negative 4 is 20. Negative 5 times negative 16 would be a plus 80. So negative 2 times 100, which is negative 200. So we get the same answer, we just had to do a little bit more work. The more zeros you can find, the easier it is to do. So you should be able to find a determinant uh, no matter how big your matrix is. And then we can use these with Cramer's rule and set up our determinants and or set up our matrices and be able to solve. So this is another method we have for solving systems of equations.